welcome to the last video in the lecture series on section 6.4. I'm going to make a definition and say a few things about the root condition and just kind of finish everything up in chapter 6, and then we'll look a little bit towards chapter 7. Let's get started. Here's the last piece of section 6.4, the actual definition. So an R-step linear multi-step method is said to be zero stable if the roots of that characteristic polynomial row that we've been working with satisfy the following conditions. So all of the roots have modulus or magnitude less than or equal to 1. And if zeta j is a repeated root, then its modulus has to be explicitly smaller than 1. And I think you've seen why in the previous examples. If the conditions in equation 6.34 are satisfied for all roots of row, then that polynomial row is said to satisfy the root condition. Quick example, and it actually covers a lot of ground. All of these Adams-Bashforth and Adams-Moulton methods that we've been actually looking at in chapter 5, those are all zero stable. There is some measure of stability about them. Why is that so easy to explain? Well, it turns out that if you look at how they are constructed, then your characteristic polynomial, your row, always looks like this, where we've got an R-step method. R is 2 or 3 or 4. You've seen a bunch of them in your homeworks and in your midterm. Well, it turns out that the roots of that polynomial are simply 0 and 1. So if I look back here at 6.34, I have a repeated root of 0, r minus 1 times, that's this piece right here, and then zeta 1 equal to 1 is an individual root of multiplicity 1, so it actually also satisfies that expression in 6.34. So it turns out that the root condition in equation 6.34 is satisfied by all of these methods, and all at once. It's not very often we're able to do that in this class. So all of the Adams-Bashforth and all of the Adams-Moulton methods are what we call zero stable. All right, a couple comments. The things that you've seen so far are meant to give you some idea as to why zero stability is defined as it is. What it doesn't say, okay, it doesn't prove that zero stability is sufficient for convergence, okay? We only looked at zero stability, only looks at this particular simplified trivial initial value problem. And we saw that even in that case, convergence might not happen if your initial conditions had some small errors. So we have to be a little careful here. Here's what we can say. So Dahlquist is one of these people who's done a lot of work in ODE methods, and he proved the following, Theorem 6.3. If I have a linear multi-step method applied to now my more general differential equation, then the thing we need to get convergence is consistency and zero stability. Okay, if you have those two things, then if and only if you get convergence. All right, so what that means is that for many of these multi-step methods that you've looked at, the ones that are consistent, well, they've got one root equal to 1, so they're always satisfying that zero stability property, so they're going to be convergent. by Dahlquist's theorem. A few other things. We call a linear multi-step method with this one root equal to 1. We call that root its principal root. It's the one that's the largest in magnitude, of course. And if I have a one-step method and I apply it to an initial value problem with f being Lipschitz continuous, then that thing is going to be convergent by theorem 6.3 up here and the zero stability that we know from the fact that that root zeta 1 equal to 1 is the only one of that character. All right, so all those methods are zero stable. One more thing, I guess, before we finish chapter 6. Zero stability, the way to think of that is stability in the limit as k goes to 0. K is our time step. So as our time step goes to 0, we take smaller and smaller time steps. Zero stability is thought of as stable in the sense that small changes, small errors in your computations as k goes to 0 are not going to do too much damage, okay? This is not the only kind of stability. So you could have a consistent zero stable method that is convergent according to theorem 6.3, but you could have some other kinds of stability problems. And those can happen when you pick a time step that's too large. And that is my motivating guide for chapter 7. All right, that is the end of chapter 6. I hope the last few remarks have motivated you to think about now chapter 7. A more general notion of stability is coming. And thank you so much for watching all these videos. I'll see you on the flip side.